तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So now let me formalize the idea of symmetry, what I mean by symmetry, what we mean by a constant of the motion and so on, and this is now going to take us into a very general relation between the concept of symmetry on the one hand, invariance on the other, and conservation laws. All these three are sort of jumbled up in our minds and they are closely linked to each other, and we will try to formalize this relationship. The first step in this regard was taken long ago by the mathematician Emmy Noether in the beginning of the 20th century. She was one of the greatest algebraists of the last century, and she discovered this theorem in a much more general context than the one I am going to give it, and the one I am going to state here applies to the simple case of Lagrangian mechanics, but the theorem itself is applicable in much greater generality. So let me write this down. Noether's theorem, and it is going to formalize the connection between symmetry, invariance, and conservation. Conservation principles, and of course leading from conservation principles is going to be is going to have conserved quantities. Such as total angular momentum or total momentum, total energy, and so on. They all follow from as special cases of this general relationship which leads from a symmetry right up to a conservation law on the other side. And Noether's theorem is going to tell us how this happens. And the idea is the following: suppose you have, to give an example, a two-dimensional motion, a particle moving in 2 dimensions, and let us suppose this particle moves under the influence of a force. So you have a two-dimensional motion on a plane, and the Hamiltonian in this case is q1 q2 p1 p2, and let us suppose these are Cartesian components, for instance. Let us suppose that this is equal to, as usual, plus a potential which would in general depend on q1 and q2, and p squared stands for p1 squared plus p2 squared. Now of course if this potential has circular symmetry, which is the two-dimensional analog of rotational symmetry, then we know that the system is invariant, the Hamiltonian is invariant under rotations in the plane. So if this is a function of q1 squared plus q2 squared to the power half, say, it is a function only of the distance from the origin, then if I make a rotation of the coordinate axes in the q1 q2 plane, the new Hamiltonian is not going to look different from the old Hamiltonian. It is simply not going to change at all. You would expect that the physics of the problem will therefore not change. What will remain invariant? If I take, for example, the Euler-Lagrange equations and solve them, what would be invariant under this set of transformations? That is, instead of choosing these coordinates q1 and q2, I choose some coordinates q1 prime and q2 prime, which is tilted, which are tilted, these axes are tilted with respect to the original axis by some angle alpha. I make this transformation and choose q1 prime q2 prime and correspondingly p1 prime p2 prime. as my generalized coordinates and momenta, what is going to remain invariant? The Hamiltonian does not change, so what would remain invariant? The differential equations would not change in form, they would look exactly the same in the new coordinates, in the new variables, as they would in the old variables. And what is the consequence of that? The equations of motion do not change in the old coordinates or in the new coordinates, they look exactly the same. Therefore what happens, can I assert that a solution does not change, looks exactly the same as before? Can I add that? Well, apart from adding trivial constants and so on, can I assert that a given solution does not change? Can I do that? Can I do that? Well, we also must be careful about initial conditions and so on. So the numerical values in the unprimed coordinates and in the primed coordinates variables are different, of course. So can you assert that the thing does not change at all? What does not change? What does not change? Is it not possible, for example, suppose, take a very simple example, suppose I have an equation x squared is equal to 4. Yes, look at this as an example, and I want you to impress upon you what the meaning of this is. I have an equation x squared equal to 4. This equation is invariant under a change of coordinates which takes x to x prime, where x prime equal to minus x. So what has remained unchanged? This implies x equal to plus 2 minus 2. You have two solutions. So what has remained unchanged? Now I look at this equation in the primed coordinates. What does it look like? So let x prime equal to minus x, then this equation gets transformed to x prime squared equal to 4. What are the solutions here? Minus 2. Suppose I look at this solution x equal to plus 2, does it remain unchanged? What happens to it? It becomes minus x prime equal to minus 2. So this solution corresponds to that, and that solution corresponds to this. So what has remained unchanged? The set of solutions is unchanged. Once you have understood that, you have understood a great deal of the secrets of the universe. Under an invariance, it is the full set of solutions that is unchanged, the solution space is unchanged. Individual solutions would go from one solution to another, but within the same set. This is the meaning of invariance, dynamical invariance always. So it is the full set of equations that is going to be unchanged. A given solution will look like some other solution after you transform, but the full set is unchanged. So therefore we now begin to understand what we mean by dynamical symmetry. The dynamical symmetry of a given system is a set of transformations of the phase space variables such that the equations of motion do not change, and as a consequence the set of solutions do not change, it does not change. So that is what I would mean by a symmetry of the system. Okay. Now let us formalize it. Let us write this down in the following way. I will do it first in the Lagrangian framework and then in the Hamiltonian framework, where it will become much clearer. So let us suppose you have a Lagrangian L of q dot, I ignore the t for a moment, it is not relevant, and I make a change of variables from q to something else. I would like to parameterize this, I would like to make a set of continuous change of variables. For example, when I rotated the coordinate system, I could have chosen a whole lot of alphas, an infinity of alphas, any number of angles, right, all between 0 and 2 pi. So I would like to parameterize the transformation by a certain parameter or set of parameters, and let us call that set of parameters alpha, and therefore let me call q of alpha the coordinate in a frame which is rotated by an angle alpha. As alpha changes, this q of alpha becomes something else. and q of 0 is my original q. I start with an original set of coordinates, and that is when there is no rotation angle at all, and then I start going to sets of new coordinates each time parameterized by a certain alpha, and let me call that q of alpha. The Lagrangian here goes into the Lagrangian q of alpha q dot of alpha, and let me call this Lagrangian L prime. L prime is equal to L when alpha is equal to 0 by definition. And now I ask, alright, how would the equations of motion remain unchanged if L prime is equal to L? They would not change, right. So let us say invariance implies L prime equal to L. Which in turn implies that dl of q of alpha q dot of alpha over d alpha must be 0. It means this Lagrangian can't depend on alpha even though you made a change of coordinates. And think of this potential problem, think of the potential as a function of q1 squared plus q2 squared. If I now make a rotation, q1 prime is q1 cos alpha plus q2 sin alpha, and similarly for q2 etc. And now you can easily see that q1 prime squared plus q2 prime squared is the same as q1 squared plus q2 squared, and therefore the Lagrangian does not depend on this alpha at all. But the consequence of this immediately says delta L over delta q dq over d alpha, because L depends on alpha through q of alpha, plus delta L over delta q dot dq dot over d alpha must be 0, because L is not directly a function of alpha, it depends on alpha through q of alpha and q dot of alpha, and this must be 0. But that immediately tells us that d over dt delta L over delta q dot, that is what the Euler Lagrange equation is for this, d over dt delta L over delta q dot dq over d alpha plus delta L over delta q dot times d over d alpha of dq over dt. But alpha has nothing to do with t, this is just a set of coordinates which I am using, a transformation, right. And if you look at the trajectory, for example, at some instant of time, if this point here is q which is equal to q of 0, if I go to a set of changed coordinates, the numerical values of these quantities would change and the new trajectory would perhaps look like this, and this point is mapped to this point if I change the alpha, and let us suppose this is an infinitesimal change. So this is q of delta alpha, a very small alpha rotation for example. Then what is this equal to? This is q of delta alpha at time t. So at some instant of time t, this is at time t, and of course this q changes in this fashion as a function of time. At a particular instant of time, I look at this coordinate or set of coordinates in the original frame of reference, in the original coordinates, and in the transformed coordinates. And if it is an infinitesimal transformation of this kind, it is quite evident that this is equal to delta q over delta alpha d alpha or delta alpha. So let us write it better, dq over d alpha delta alpha. So this alpha has nothing to do with t, it is just changes of frames of reference or coordinates. Therefore you can write 0 equal to this equal to d over dt delta L over delta Q dot dq over d alpha plus delta L over delta Q dot d over dt of dq over d alpha, which of course immediately is d over dt of delta L over delta Q dot dq over d alpha, and that is 0. So what does that imply? The quantity in the brackets is a constant of the motion. This implies immediately that delta L over delta Q dot dq over d alpha equal to constant of the motion. It is conserved, and therefore I can evaluate it at any instant of time, including t equal to 0 in the original coordinates. But in the original coordinates, what does this become? What is delta L? So this becomes delta L over delta Q dot, and what is that equal to? This quantity here, it is the original P. So this is equal to P dq over d alpha at alpha equal to 0. I can evaluate it at any instant of time, including t equal to 0, and therefore even the slope dq over d alpha I must do at alpha equal to at t equal to 0. So that gives me a prescription for finding the constant of motion corresponding to invariance. I can generalize this to many variables now, so not just a single alpha but a whole set of alphas. If I rotate in 3 dimensions, for instance, I would have 3 rotation angles, and then I would have 3 constants of the motion corresponding to 3 angular momenta. We will work this out in terms of some simple exercises, but this is the idea of Noether's theorem. Is this the most general way you can write this theorem? Is there something else you can do which immediately generalizes the theorem? Well, remember that I said that a Lagrangian is not unique. You can add the total derivative of a function of the generalized coordinates and time to it, and nothing is going to happen. Total time derivative could be added to it. Therefore it is not necessary that invariance implies that L prime equal to L. So how could L and L prime differ and still get away with the fact that the equations do not change? You can add a df over dt to it, right. So you work through the whole thing again by saying L prime is not equal to, this is not equal to 0, but the difference L prime minus L to first order in delta alpha equal to df over dt. You plug that whole thing back again, and then you discover there is an extra contribution here which would depend on f, and that is the most general invariance you could have. This is the content of Noether's theorem. What is absolutely crucial for it is that the set of transformations must be continuous. We have differentiated with respect to that parameter, and they must be connected to the identity. In other words, you must have a situation where you have the original coordinates and then you make a transformation which takes off continuously from no transformation at all. So this is a connected set of transformations. Parity is not one, is not such a connected set of connected transformation, it is not a continuous transformation, because if you go from a right handed coordinate system to a left handed coordinate system, you cannot do so continuously, it is a discontinuous transformation. But rotation is a continuous transformation, a shift of the origin is a continuous transformation, a shift of the origin in time is a continuous transformation. Is there any other continuous transformation you are familiar with? You can scale things out. I can always multiply the coordinates by constants, I can shear the coordinates, I can do all sorts of linear transformations. Is there anything else, any other physical example of a continuous transformation which has nothing to do with the coordinates? Well, they are all on the coordinates, these are all transformations induced on the coordinates, but there are other transformations. For example, if you go back to the example of a charged particle in an electromagnetic field, you can make a continuous set of gauge transformations. it could be continuous, right. You could start with an infinitesimal chi and then keep going, and that would again be a transformation which would lead to a conservation principle. In this case it leads to the conservation of charge. So at last we begin to understand where the conservation of charge comes from. It comes from the gauge invariance of the electromagnetic field equations, of the equations of electromagnetism. So this is really the principle that underlies what the conservation law is trying to tell you. Okay. Now having done this, we will work out an example with regard to this application of this Noether's theorem. Yes. You can evaluate it at any point. The point is, at any point, the whole idea is I would like to write it in terms of a quantity which I know, which is p, but of course this p I need not have started with my original coordinate system like this. I could have started like this at some finite value of alpha. I call that my initial p and q, so it does not matter. The whole point is both terms in this bracket have to be evaluated at the same value of alpha. It is quite clear. You can't do this at different values, right. So if I did it at alpha equal to 0, the other term also had better be done at alpha equal to 0. That is the only point I am making, right. Now you could ask, alright, so much for the Lagrangian situation. To summarize, what has happened is we have found if the Lagrangian is invariant under a continuous set of transformations, then Noether's theorem tells you there exists a corresponding conserved quantity. There are as many conserved quantities as there are parameters for the transformation. In 3-dimensional rotations there are 3 Euler angles which are the parameters, and therefore you have 3 conserved quantities. If you shift the origin in 3 dimensions, once again there are 3 constants by which you can shift the origin, one for the x, one for the y, one for the z direction, and therefore there are 3 constants once again, and they would turn out to be the components of the linear momentum. For rotations it is the angular momentum. You can even change the origin of time, and if the equations of motion remain unchanged, then it means that there is a constant of the motion, a Noetherian constant of the motion, and that is the Hamiltonian itself. So each time you see that conserved quantities arise as a consequence of this principle. There is a certain symmetry in the system which leads to an invariance of the equations of motion, and therefore the set of solutions which leads to a conservation principle. Now let us go and ask, in the Hamiltonian framework, what does this look like? What would this mean? What would the constant of the motion imply? And that is even more interesting, and let me do that. A little bit of preliminary work is needed. So let us look at it in the Hamiltonian. In this framework I have a Hamiltonian function of the generalized coordinates and generalized momenta. I am only going to look at autonomous systems for the time being, and I know that the equations of motion are such that q dot is delta h over delta pi, pi dot is minus delta h over delta qi, and I also know that there exists canonical Poisson bracket relations This ensures my standard structure, Hamiltonian structure. And now I make a transformation which leaves Hamilton's equations of motion invariant, otherwise you do not have a symmetry at all to start with. What set of transformations leaves Hamilton's equations unchanged? Canonical transformations. So it is quite clear that whatever symmetry transformations we are talking about must to start with be canonical transformations. Okay. That may not be enough, you have to start with canonical transformations. So this thing here must go over into something which looks like qi dot equal to delta k over delta pi delta qi, and moreover you must have qi pj equal to delta ij. this ensures that it is canonical. But for Hamilton's equations to remain unchanged, the Hamiltonian must remain unchanged so that the set of solutions look exactly the same. So you need something more, you need those canonical transformations for which k is the same as h, otherwise it is not going to be a symmetry, it goes into some other Hamiltonian and that is not a symmetry transformation. So a dynamical symmetry transformation is one where Hamilton's equations not only remain unchanged in form and the new q's are canonical coordinates, but the new q's and p's are canonical variables, but the Hamiltonian itself does not change in form. The functional form k must be the same as the functional form h. But even without that, this is what a canonical transformation is. Now can we say something more about it? What kind of transformations are canonical transformations? So let us look at that. We need to understand that. How do we do this? Well, let us suppose x equal to the q's and p's, q1 to qn, p1 to pn, and let us suppose you make a canonical transformation to a new set of variables, and let us call it c, which is capital Q capital P. Okay. Once again I work in this 2n dimensional phase space and I have these Poisson bracket relations. Now what do these bracket relations imply? For example, this relation, what does it mean? It says qi pj equal to delta ij implies this is equal to a summation from k equal to 1 to n delta qi over delta qk delta pj over delta pk it implies this relation because that is what is the meaning of the Poisson bracket. So it says that this set of relations must be true. When you calculate this Poisson bracket of the new q's and p's, you are going to have to get delta ij, but that is our definition of the Poisson bracket, and it says this quantity must be equal to delta ij. It further says qi qj equal to 0, so you are also going to have qi qj equal to 0 and pi pj must be equal to 0. So that equal to a similar relation with qj here and qj there, and similarly pi and pj there. So you have all these three sets of relations must be valid, otherwise it is not a canonical transformation. Now that looks very messy and you could ask, what does this mean? What does this finally mean? Is there a simple way of understanding it? The answer is yes, there is. Recall that we had defined this matrix J, which was equal to 0 unit matrix minus unit matrix J 0, and I put an n here to show these are n by n matrices. We defined this matrix J, and then I said Hamilton's equations take on a very simple form, and the form that this set of equations took on here was x dot equal to J gradient of h. It is an extremely simple form that they took on. So this full set of equations can be summarized in just that single line here. And of course when you make a canonical transformation and go to q and p, then once again this thing here would say is c dot equal to j gradient of k, but the gradient in the new variables. So gradient with respect to the components of c and with respect to the components of x. So these are very simple structures, and now you can ask, we also saw that the Poisson bracket of a with b could be written as the gradient of a transpose j, the gradient of b. So you can ask, can this set of equations be written in a simple form? And the answer is yes. You can take the Jacobian matrix delta c over delta x. This stands for a 2n by 2n matrix in which each component of c is differentiated with the corresponding component with the components of x here, and you have a 2n by 2n matrix. that is the Jacobian matrix for the transformation. That matrix transpose J, and that matrix once again must be equal to J, and that is what the content of this set of equations is. A little bit of work and you can write down the entire set of canonical transformations. Any canonical transformation is canonical if and only if this Jacobian matrix J, the Jacobian transpose J, the matrix equal to J itself. Okay. Suppose you did not have this, then it says matrix transpose matrix equal to the unit matrix. What do you call such a matrix? Transpose R equal to I. Well, you do not call it unitary, you call it orthogonal. If it is real, then of course a unitary real matrix which is unitary is orthogonal. It says matrix transpose equal to inverse of the matrix, that is an orthogonal matrix. This is not quite orthogonal because there is this J sitting there always. I call it pseudo orthogonal. It is like an orthogonality condition. We should by now expect this J to appear everywhere, to pop up everywhere in Hamiltonian mechanics. It is acting like some kind of metric in the space of Q's and P's. So this is the generalization of the condition of orthogonality. We call it pseudo orthogonality. There is a name for all such matrices. So let us look at all matrices if a matrix M transpose J M equal to J, and M is called a symplectic matrix. And of course this J has got marvelous properties, because recall so any matrix that satisfies any 2n by 2n matrix, phase space is always even dimensional in Hamiltonian mechanics at this level. So any even dimensional, any 2n by 2n matrix which satisfies this condition is called a symplectic matrix. And now it is a simple matter to prove that every symplectic matrix has an inverse. That is obvious from here actually. What is the inverse of M? Well, all you got to do is to use this once again, and it is going to be related to M transpose. Just as if it were orthogonal, M transpose would be M inverse. Now this is not quite true, it is related to M inverse is related to M transpose with J's on either side and so on. Okay. So symplectic matrix has an inverse, and we know a canonical transformation must have an inverse transformation, so it better have an inverse. Then the next thing you can show is that the set of symplectic matrices form a group. The product of two symplectic matrices is also a symplectic matrix. Physically, what does that imply for canonical transformations? I make one canonical transformation and then make a second canonical transformation, it is equivalent to a single canonical transformation. So there is an inverse and there is a composition law, and these transformations form a group. So the set of canonical transformations for an n degree of freedom Hamiltonian system form a group. It is the group of 2n by 2n symplectic matrices, and this group has a name, and this group is called SP2n, and since we are working on the reals, because you can complexify the whole thing, it is called SP2n comma R. That is the group of canonical transformations. No, a symplectic matrix cannot be singular, it has an inverse, it is guaranteed to have an inverse. Is J a symplectic matrix itself? J itself is 1, you can see that right away, because if I put J transpose, that is the same as minus J, but J squared equal to minus identity, so this says J equal to, of course it is true immediately. What is the canonical transformation corresponding to choosing that Jacobian matrix to be J itself? Q equal to minus P, P equal to Q, the one we did yesterday, that is the transformation. So that was the simplest of transformations, the first canonical transformation you can think of, where the coordinates and momenta were actually interchanged with the minus sign, and that corresponded to choosing M equal to J itself. Now this is a fairly large group, every group of matrices has a certain number of parameters, independent parameters. The group of rotations in a plane has one parameter, the rotation angle. The group of rotations in 3 dimensions has, in 3 dimensions, 3 parameters. The group of rotations in 3 dimensions has 3 parameters. There are 3 Euler angles which you need to go from any coordinate system to any other by rotation. So it has 3 real parameters. We say that the group of orthogonal matrices with determinant plus 1, SO3 in 3 dimension SO3 has 3 parameters. How many parameters does the group of rotations in n dimensions have? It is the group of orthogonal matrices in n dimensions with determinant plus 1. You would like to look at proper rotations. How many parameters does that have? How many angles are needed to specify a rotation in n dimensions? N angles? Why do you say that? That's a good guess. Why do you say n? Very good point. With respect to each axis you rotate, and each axis there are n independent axes, and therefore his argument is you have n angles. But what happens in 2 dimensions? There is only one angle. How do you say that? How do you define a rotation in 2 dimensions? What is a rotation in 2 dimensions? 2 Euclidean dimensions. Rotation, where is the z? There is no z. About the origin. Rotation about the origin. So it is rotation about a point. There is no axis. It is rotation about a point. Rotations are a little trickier than you imagine. So let us do that. In 2D, I rotate from this set of axes to that set of axes parameterized by a single alpha here. So here is x, y, here is x prime, y prime. So the group of rotations which comprises the group of matrices which are orthogonal, real entries, and has determinant plus 1 can always be written in the form this contains. So all matrices of the form SO2 contains all matrices of the form cos alpha, sin alpha, minus sin alpha, cos alpha, right. And what does a rotation do? It takes the xy, takes the original coordinates, makes each goes to a new set of coordinates. Each of the new components is a linear combination of the old variables, and it is homogeneous. The set of transformations is homogeneous because the origin remains unchanged, no constant is added, not a translation rotation. So a linear homogeneous transformation which leaves a point unchanged, the origin unchanged, therefore it is homogeneous, is a rotation. It must have determinant plus 1, otherwise the axes get flipped, the handedness gets flipped. So linear homogeneous transformation which has determinant plus 1, it is called unimodular, is what a rotation is. Now how do you define a rotation in 3 dimensions? What is the basic property of a rotation? It leaves lengths unchanged. The distance between any 2 points is unchanged. That is the basic property. So all you need to define a rotation is it should be a linear transformation, it should be homogeneous. Without loss of generality we say let the origin be unchanged, it should leave distances unchanged, therefore it must be orthogonal, the transformation must be orthogonal, that is a necessary and sufficient condition. It must be specified by an orthogonal matrix that is necessary and sufficient to ensure that distances are unchanged, and it must have determinant +1. That is it, that is all you need for defining a rotation. Now suppose I am in 4 dimensions and the coordinates are x1, x2, x3 and x4, let us say. I rotate in the x1, x2 plane and I leave x3 and x4 unchanged. Is this a rotation or not? Yes it is, but which axis have I rotated by? About which axis have I rotated? I have left the whole of the x3, x4 space unchanged. So a rotation is not defined by saying you rotate about an axis. A rotation is a linear transformation which is homogeneous, orthogonal and unimodular, and that is it. That is the general definition of a rotation. It applies to all dimensionalities. Yeah, that is how we define a rotation. That is not part of a rotation, that is a separate transformation altogether, right. So if I include translations the group gets enlarged to what is called the Euclidean group. Right now I am talking only about rotations, about homogeneous transformations, and I am trying to define a rotation appropriately in a rigorous way.
So the basis of choosing these were that the lengths would remain unchanged.
Yes, yes.
I don't see how these conditions are sufficient to make sure that only rotation leaves lengths unchanged, that there is not any other transformation.
Oh no, that is a good question. I am not saying that at all. I am not saying a translation would change lengths and so on. I am not saying that. I am saying what is the set of homogeneous transformations that leaves lengths unchanged? You have to have orthogonality, okay. And if I want to leave orientations unchanged you must, or handedness unchanged, you must also have unimodularity. Every orthogonal matrix has determinant either +1 or -1. And you choose the +1 for the proper transformations. If you include reflections then it is -1. Alright, so that is my definition of a rotation. You cannot always associate an axis with a rotation. In 3 dimensions what you can do is associate a plane. You can always say every rotation can be regarded as rotation in some plane, does not have to be one of the Cartesian planes, could be something tilted at an angle, but there is always a plane. So 2 variables are affected at a time. Now therefore tell me, since 2 variables are affected at a time, how many rotations are there? NC2, right. So it is n times n minus 1 over 2, that is the number of angles you need to specify a rotation in n dimensions. And what is it for n equal to 2? 1. And n equal to 3? 3. It turns out that this quantity n times n minus 1 over 2, which is the number of independent planes that you can have, orthogonal planes, happens to be equal to n when n is equal to 3. This is a great accident, well maybe not such a great accident after all, and that is the reason you say this rotation about the z axis, about the x axis, about the y axis, because you are really saying rotation about the y in the yz plane, the zx plane and xy plane, but you can't do this in any other dimensionality including 2. This has a solution in integers only for n implies n equal to 3. So one of the reasons why 3 dimensions is very special, okay. So how many generators does SON have? In exactly the same way you could ask how many generators does the symplectic group have? How many possible parameters do you need to specify all possible canonical transformations? And the way to do this is exactly what you did for rotations, namely ask, if I make an infinitesimal transformation, how many parameters are there? How many independent ways can I make infinitesimal transformations? So let us make an infinitesimal transformation out here. So let us say m is equal to the identity transformation plus some epsilon, some small parameter like a delta alpha times g. G is some other 2n by 2n matrix called the generator of the transformation. Plug that in here and what do you get? This implies I plus epsilon G transpose J I plus epsilon G equal to J, and let us open it out, and you have to retain to first order in epsilon, and what does it tell you? It says, so if you multiply this through, it is J plus epsilon G transpose J times I plus J epsilon G equal to J, dropping the epsilon squared term, and the J cancels out. And the epsilon drops out. Okay. So symplectic transformations are generated by matrices which satisfy this property. G transpose is J minus J, G transpose J is minus JG, and let us take the J to the right hand side. So this becomes J inverse, but J inverse is minus J, therefore this. So the generator of a symplectic transformation, the infinitesimal generator, must satisfy this condition. The transpose of this generator must be equal to J G J, and now you can count how many parameters it must have. So I leave this as an exercise to you to show that SP2n has twice 2n plus 1 generators. It is much larger than the, yeah.
What is definition of a generator?
Well, I haven't quite defined what a generator is, but the way I would like to look at it is, if I look at what happens here for an infinitesimal rotation, then let us replace this cos alpha by delta alpha, sin alpha by a delta alpha, and work to first order in delta alpha. Now what is cos delta alpha to first order in delta alpha? 1 minus delta alpha whole square over 2 factorial, but then I am working to first order, so cos alpha is just 1, right, and this is equal to 1 delta alpha minus delta alpha 1 to first order in delta alpha, which is equal to the identity matrix plus delta alpha times 0 1 minus 1 0. This is the parameter, and you can change it, but that is a given matrix, and that matrix is what I called a generator. Now the question is, find out how many such independent matrices are there in general, and in 3 dimensions it is not hard to see that there would be 3 of them. For rotations, for the symplectic group there would be twice 2n plus 1. Okay. This is a large group, so you have got all kinds of transformations possible as infinitesimal as canonical transformations. It is a fairly large group. We will say a little more about it here. I will come back and spend some time on the rotation group and its generator and so on, because that is not quite the way I would like to write the generator. I would like to write the generator as a Hermitian matrix, and the reason is I would like to exponentiate this generator, and when you exponentiate a Hermitian matrix, what do you get? E to the power I times a Hermitian matrix is a unitary matrix, and the unitary matrix has interesting properties. It is the analog of canonical transformations in classical physics. So we will do a little bit of this subsequently, but right now the point I want to make is that the group of canonical transformations can be related to a group of matrices. As you can see, they are generated by this symplectic group. Okay. But now I pointed out, coming back to our original problem, the symmetry group of a dynamical system is that set of transformations which leaves the set of equations of motion unchanged, and therefore the set of solutions unchanged. Now in the Hamiltonian framework, you first needed to ensure that the structure of Hamilton's equations did not change, so you needed to ensure that they were canonical transformations, but you also need to ensure that these transformations do not change the Hamiltonian itself, that the k was equal to the h itself. And what would you expect that to be? I would expect that this dynamical group, the symmetry group, would be a certain subgroup of the symplectic group. Some canonical transformations would not change the Hamiltonian, and that would be my symmetry group. So this is the expectation, and the best way to do this is to do this in terms of an example. So let me do that. Okay, and let us look at a simple example. 2D oscillator. And let me choose again a 2-dimensional simple harmonic oscillator for which we understood the motion. It is going to be on some torus, and it could be periodic, it could be quasi periodic, but look at what happens. Let me choose the mass to be equal to 1, and let me choose the frequency of one of the oscillators to be 1. So I write the Hamiltonian Q1 Q2 P1 P2 to be equal to 1/2 Q1 squared plus P1 squared plus omega squared Q2 squared plus P2 squared. So I chose the frequency here to be 1 and the other guy to be omega, and this in general immediately led to quasi periodic motion. In fact, it was not periodic even if omega was irrational. When omega became rational, it is periodic motion, but still fairly complicated. Is it a central force? Is this a central force? If I imagine Q1 and Q2 to be the x and y coordinates of a particle, and it is attached by springs, 2 springs here at right angles, then when is it a central force? When both are exactly the same spring constant, then the force is always directed towards the origin, right? And what would that imply here? What should it be? Omega equal to 1. I would have to put omega equal to 1. So I do this here, and this is called the isotropic oscillator. Why do I call it isotropic? The same force in all directions, independent of the direction, it is always got the same spring constant. It is the same in all directions on the plane. So this isotropic oscillator has an extra symmetry, and what is the symmetry? It is obvious here, look at it. It has circular symmetry, rotational symmetry, not true for the non-isotropic anisotropic oscillator. So it has got an extra degree of symmetry, this problem. What set of transformations leaves the Hamiltonian unchanged? It is obvious from this form. Q1, Q2, P1, P2 are 4 real numbers running from minus infinity to infinity. What transformations would leave this unchanged? Rotations not just in physical space, rotations in phase space, the 4-dimensional phase space. So the Q's and P's could get mixed up, does not matter, but the Hamiltonian would remain unchanged. What group of rotations is that? I mean, what group is that set of rotations? It is SO4. So H is invariant under SO4. This is not a group of transformations in physical space, it is a set of rotations in the 4-dimensional phase space. So the first lesson that comes out is that you could have dynamical symmetry arising as a consequence of transformations not just of the potential, not just in physical coordinates, but it could also involve the momenta. So that is the real set of transformations. So how many generators does SO4 have? 6 generators, right? So lots of transformations. What is the set of canonical transformations of this system? It is SP what? Well, n equal to 2 in this problem. So this is SP4. 4 by 4 symplectic matrices. because the phase space is 4 dimensional. How many generators does that have? Twice 4 plus 1 equal to 10 generators. So it is clear these are different groups. So it is clear immediately from this that all transformations which leave the Hamiltonian unchanged need not be canonical transformations, and similarly all canonical transformations on this system need not leave the Hamiltonian unchanged. For a symmetry you need both these properties, so you need some subgroup of this symplectic group which contains the other group there, but all members of the other group need not be sitting here at all. So it is like this. Symbolically this is sp4 and this is SO4. So what should I choose to be the symmetric group? The intersection of these groups, and that is guaranteed to be a subgroup of the symplectic group. I am not going to prove this, but it turns out the symmetry group of this system here, the dynamical symmetry group, is the intersection of sp4 intersection with SO4, and that is isomorphic to, or at least is one-to-one correspondence with, the following set of transformations. This is isomorphic to a group called SU2. Okay. It is a set of 2 by 2 matrices which are unitary and have determinant +1. The matrices could have complex entries, does not matter, but it is a set of unitary matrices. What is the definition of a unitary matrix? Implies complex conjugate transpose called the Hermitian conjugate U dagger on U must be equal to the identity matrix. In other words, the inverse is equal to the Hermitian conjugate, not the transpose alone but complex conjugate transpose. That is a unitary matrix. Is this also true? Is this also true? For finite dimensional matrices this is true, because the left inverse is equal to the right inverse for finite dimensional matrices, but if these are infinite dimensional matrices then there is no guarantee that U dagger equal to I implies U dagger U equal to I, does not imply that at all, but we are concerned with finite matrices, so it does not matter, finite dimensional matrices. Incidentally, just for information, U dagger U equal to I simply says that you have a property called partial isometry, and similarly U dagger equal to I says you have partial isometry. One of them says you have a left inverse but not a right inverse, and the other, and vice versa in the other case. But if both these are true, then you have complete isometry, which is also called unitarity, then you have a unitary matrix, but otherwise it is partial. In our finite case it does not matter, this implies that. And now we are saying that the dynamical symmetry group of this 2-dimensional harmonic oscillator is that set of matrices which is that set of transformations which is in one-to-one correspondence with the group of 2 by 2 unitary matrices with unit determinant. And then the next question to ask is how many generators does that have, and what are these generators? And next time, since I have run out of time, we will write down what the generators are, and meanwhile I will leave it as an exercise to verify that the following is true. Verify that in this problem the following are constants of the motion. J1 is 1/4 q1 squared plus p1 squared minus q2 squared minus p2 squared. J2 is 1/2 q1 q2 plus p1 p2, and J3 equal to 1/2 q1 p2 minus q2 p1. Verify that Ji H equal to 0. These are constants of the motion, but they are not in involution with each other. So verify that Ji Jj equal to epsilon ijk jk. So Poisson of J1 with J2 is J3 and so on in cyclic permutation. They are going to turn out to be the generators of our dynamical symmetry group. They are not in involution with each other, and then we will see where that fits in here. So even the humble 2-dimensional oscillator has a great deal of deep mathematics in it at some level, and our aim actually is to use this as an example and then go over to the Kepler problem, the 1 over r potential, which has an even better symmetry than this. So that is my next target, but this is a preliminary required for that. So let me stop here.